Okay, so last time we talked about the theory of solutions when the solutes don't interact very strongly with each other. So we're talking mostly about the case that I've drawn here, where the molecules are there, they run around in solution, their entropy matters, and that contributes a lot to the chemical potential. But they don't really interact with each other. They don't clump up. They don't repel. And that's good for the vast majority of solutions. But for ionic solutions, where you have charged particles running around in solution, then there is this very strong electrostatic interaction, both between positive and negative, so attractive interactions between positive and negative, and repulsive interactions between positive or negative and negative. And that changes the picture quite a bit. The chemical potential formulas that we've been using so far kind of maybe okay, work still if you don't do anything else, if you just use them straight. But they don't work very well. Big mistakes can be made. We'll see some examples of that at the end of this section. So down here is our standard equation of state for chemical potential. It depends on this mysterious activity. We've talked about that. It's a measure of concentration. The reason that's in there is mostly for this case. The reason we don't just put concentration in there is because in this case, which is very common, ionic solutions are almost one of the most common kinds of solutions there is, maybe the most common kind of solution. That activity in that case really isn't just concentration. It's seriously different from just concentration. We have to correct for the fact that it's not just concentration, and that's what this whole section is going to be about. So nominally, we're going to correct by saying that the activity is concentration like normal divided by the standard state concentration, of course, but then also multiplied by this fudge factor that I've talked about before, this activity coefficient. Oftentimes those activity coefficients in other kinds of situations really are just constants. You look them up in a table, or you measure them or something like that. But in this case, in the case of ionic solutions, it's also something that depends on concentration. So this whole thing is not just, proportional to concentration alone. It's proportional to concentration and then whatever dependence on concentration is hidden inside of this gamma. And it's finding that hidden dependence that we're going to talk about now. All right, so the core theory, the original theory that generated all the ideas for which theories of ionic solutions have since been developed, is Debye-Huckel theory. It's not very accurate except at really low ionic strength, really low ionic concentrations, but it has all the right ideas. It's got all the right pictures. And for our purposes at the moment, that's the most important thing. We'll look at some better theories at the very end, but Debye-Huckel theory and the related theory called Poisson-Boltzmann theory are going to be plenty good enough for us for the moment. So here's the physical picture. You've got this ion floating around in solution. It's a positive ion in this picture, but it could be negative. And because it's a charged particle, it has surrounding it something called an electrostatic potential. And I know that idea is unusual for chemists, so let me talk about it a little bit. Basically, the electrostatic potential is something we're all familiar with. I have a little note over here to the side in yellow. If I have a point charge, and then there's some distance to another point charge, we all know that the potential energy of interaction is some constants times 1 over r, right? The potential energy of interaction between two charges is a 1 over r kind of potential function. That's an example. This is essentially an electrostatic potential. That's an example of a potential. They get much more complicated. If you have some arrangement of charges that's really complicated, there's always a potential. It's not always this nice simple one. And in fact, we're going to see a more complicated one now. but there always is one. You can always get it. It's potential energy of interaction per unit charge. So if I have the potential energy, the electrostatic potential here, and that's the blue stuff that I drew in, and then I multiply it by the charge of my incoming charge, then this is the energy of interaction between these two charges. So I don't have to worry about what's down here. If I know this function, this can be some complicated big mess of charges. As long as I know the potential, I can multiply that potential function by the charge that's coming in and get out the energy of interaction between the mess and the incoming charge. That's the strength and the main reason for defining this funny function called the electrostatic potential. Let me just point out one thing because we're going to need it later. I'm going to write all the charges on all the ions as an integer z, which I've written a little bit about over here, times the charge on an electron. So basically z is the charge on the ion in electron units. It's +1 for a sodium ion, it's -1 for a chloride ion, it's +2 for a calcium ion, and so on. It's the usual charges that we normally talk about on ions. All right, so what's going to happen then is because plus charges attract minus charges, in ionic, and because the interaction is strong, in ionic solution, there's going to be a strong tendency for minus charges to hang out closer to the plus charges than they would if they were just free in solution. And likewise, the plus charges will hang out near the minus charges more often than they do in solution. So the way we understand that is that there's around every ion, everything like this positive central ion, there's a counter-ion atmosphere. It's a statistical idea. This isn't really smeared out charge. It's the statistical distribution of all the minus charges that are hanging out, having a tendency to hang out more closely to the positive charge than they would if it were just bulk solution. So this red area is, this cloud is a statistical distribution of counter-ion charges. And that statistical distribution plus the central charge on the central ion together form the charge distribution that gives rise to this electrostatic potential I talked about above. And so our task is going to be to find that electrostatic potential for a reasonable length, for a reasonable situation in a reasonable solution to reasonable accuracy. We're not going to get something that's really close to true. Here's the central equation that we're going to solve. It's called, well, an approximation of it is what we're going to solve. It's called the Poisson-Boltzmann equation. Poisson-Boltzmann equation didn't used to be very important. It is very important now. It's widely used in practically every molecular simulation that's run, and molecular simulations are run very commonly in any kind of research setting, even in a lot of industrial settings these days. So what is the Poisson-Boltzmann equation? Well, it's got two parts. So the two names actually correspond to the two parts of the Poisson-Boltzmann equation. One of them is something called the Poisson equation, which comes straight from electrostatics. It's one of the Maxwell equations. It's one of the basic equations of electrostatics. What it says is that if I have this potential function, this electrostatic potential, and I take a del squared operator on it. So I hope everybody's happy with del squared operators since you guys all had quantum mechanics last semester, and it shows up a lot in quantum mechanics. Then you get the charge density that created this electrostatic potential. So you take this del squared operator on this potential function, and you get out the charge density, or working backwards, you start with the charge density, let's suppose, and then you can solve this, what amounts to a partial differential equation, in order to get the potential. Either way you can go. So far, that's just electrostatics. There's nothing Poissonian about it. There's nothing Boltzmann about it. Over here is what we're going to say our electrostatic potential is. It's a sum over all the types of ions in solution of the charge on each type of ion times a quantity, all of this stuff, which amounts to a modification of the local counterion concentration. In other words, this part of it is the thing that's accounting for the fact that there ought to be more minus charges near this plus charge than there would be in bulk solution, and vice versa. There ought to be more plus charges near every minus charge than there is in ordinary solution, in bulk solution. So the two pieces that are in this term are the particle density for each type of ion. That's basically a concentration. It's a little bit different than the normal kinds of concentrations we work with, but don't worry about it. We're going to convert it to molar concentration pretty quick here anyway, so just leave it for now. And then there's this probability factor. It's a Boltzmann factor. We haven't talked about statistical mechanics yet. That's coming soon, actually. Now, I've been saying all semester that statistical mechanics is important. Here's maybe the very first instance we've seen where statistical mechanics is actually used. A Boltzmann factor calculates probability. This thing up on top here is energy. This is thermal energy that's available. This is the energy of interaction between two particles. This is the thermal energy, and so basically this is the ratio of the interaction energy to the thermal energy. And you can kind of see maybe how that would give rise, or be important anyway, for calculating the probability of finding an ion, two ions close to each other. All right, I won't say too much more about that because we haven't done stat mech yet, but that's the idea. So there's a modified, basically, concentration of counterions for each type of ion that's in solution. We sum all those up, and that's our charge density. Now we plug that into here, and now we've got an equation that we've got to solve. That's the Poisson-Boltzmann equation. All right. I said most of all this already. Poisson-Boltzmann equation didn't used to be very important. Now it is in all these areas, biology especially. It's used widely in every molecular simulation for a protein or a DNA, pretty much. In electrochemistry, we'll see that next chapter. Next chapter. In materials chemistry, ionic solutions all over the place. In just general chemistry of any kind, ionic solutions very common. Simulations with the Poisson-Boltzmann equation are widely used now in all those areas. All right, now, we've got to solve this Poisson-Boltzmann equation. But the way it is at the moment, it's really hard to solve. And the thing that makes it hard to solve is this Boltzmann factor, which makes it a highly nonlinear partial differential equation, because the thing we're trying to solve for, this potential energy function, is up in an exponential. It's really nonlinear. So we're going to linearize it. We just basically say, all right, let's not try to solve every case. Let's just solve the cases where this stuff up on top is small compared to KT. And then we can just keep the first two terms in an expansion of this exponential. And that's only good when the interactions are weak, when this energy of interaction is small compared to KT. But fine, we can learn a lot anyway, despite that. In fact, this is usually the case people do. You take the case you can solve, you learn what you can from that case. Usually you learn a lot from those kinds of cases. And then you come back later and do the harder cases that are maybe more accurate. But all the qualitative understanding is usually buried in those easy cases anyway, and that's important. If I do that, and if I plug this approximation now into our expression for the charge density, this first term, when I do this sum, this first term is going to disappear because it turns out to be just this sum, which is the sum over all the charge densities of all the ions in solution, and the net charge density of all the ions in solution is 0. It's got to be an electrically neutral solution. So that first term disappears. Only this second term survives. And then this electrostatic potential cancels out. It doesn't have any I on it. It isn't part of this sum. And so it just factors out. The sum turns into just a big constant. It's okay, it's still a sum, but it's just a sum of constants now. And so all this stuff just becomes constant times the electrostatic potential that we're solving for, and we write it as a constant. So I've now introduced this quantity called kappa, which is a constant in its own right, and it's basically just hiding all this complexity in here. But it's an important quantity in its own right. We'll talk a lot about that kappa later. It's closely related to something called the Debye length, which basically controls everything that goes on in ionic solutions. So 1 over kappa actually is the Debye length. All right, if I now take this and plug it into our original Poisson-Boltzmann equation, then I get the Debye-Huckel equation, which is the equation that we actually want to solve. Now it's a linear partial differential equation. Actually, it's something called the Helmholtz equation. In the generic sense, the Helmholtz equation shows up all over the place. This is one particular case where it shows up. And now it's much easier to solve. Let's solve it then in 2 special cases. First case is where we're considering a situation like this one. We've got I put conductor here, but it doesn't have to be a conductor, some kind of flat surface that's charged for some reason. If you apply a voltage to a conductor, that's one way to charge it up. But down here you can see the glass surfaces have charges because they have chemical groups on their surface that are charged. And down here, colloidal particles have charges, cells have charges, lots of things have charges just naturally. The case where there is a conductor and you're applying a voltage, that's electrochemistry. That's next chapter. We'll talk about that case quite a bit, but it's only one of many cases. All right. If you have that case and then you solve the Debye-Huckel equation, you get this solution for the potential. And now remember from up here that the charge density, that is the counterion atmosphere that we're interested in, is just proportional to the potential. So when you're solving for the potential, you're solving for the charge density that we're mostly interested in. So that's great. There's some constants in front. Let's not worry about those. They're not important. The important part is this exponential decaying function down here. So z is the distance away from the surface. And this is saying that the counterion, well, down here is probably better to look. Here's the actual charge density. The counterion density, the counterion atmosphere, is decaying away, becoming weaker and weaker as you move away from the surface. That's not surprising. It's decaying exponentially. That's not too surprising. Exponential decays are utterly common in many applications, many areas of physics and chemistry. The important thing is how fast does it decay? And it decays with this characteristic decay constant, which is given by 1 over kappa, that constant I pointed out before, and which is, yes, called the Debye length. And so the thickness of the counterion atmosphere around the surface, away from the surface, is about 1 Debye length. Whatever that Debye length happens to be. Now, kappa here depends on the concentration of ions in solution via something called the ionic strength that we'll get to in a minute. So this Debye length also depends on concentration, and that means this layer gets thinner for high concentrations of ions, and it gets wider and thicker for low concentrations of ions. It basically spreads out when there's not many ions around. It bunches up when there are a lot of ions around, as you can kind of understand, right? Because if there's lots of counterions around, it's easier to pack them into a thin layer than if there's not very many. And so, yes, this thickness varies some depending on the concentration, but for typical concentrations, about 0.1 molar or so, it's typically around 1 nanometer. And if you go to very much lower concentrations, it spreads out to a few nanometers. If you go to very much higher concentrations, it shortens up to a few angstroms. But that's pretty much the range of it. Somewhere between a few angstroms and a few nanometers is the typical size for a typical Debye length. So what is this telling us? It's telling us, this is the bottom line here, that when you're in ionic solutions, every charged surface is coated or canceled, if you like, countercharged with a counterion atmosphere that's about a nanometer thick, typically. And so if you've got a glass surface, there's a counterion atmosphere that's screening or shielding all of those minus charges that come from the little silanol groups that hang out on the surface of SiO2, right, glass, right? If you stick a metal electrode into solution, because you're going to do some electrochemistry, and charge it up, you apply a voltage, that creates all these charges here, then there's a counterion atmosphere that comes right after the charges appear and cancels all those charges, or tries to cancel all those charges, basically does cancel all those charges. And that's extremely important in electrochemistry. I'll make this point now because we're going to make it again next chapter, and it's an important one. And that is, electrochemistry only works in ionic solutions. Why? Because only in ionic solutions do you get this Debye-Huckel counterion atmosphere, and you need that counterion atmosphere in order to make electrochemistry work. You may say, why? Why do I need this counterion atmosphere? We'll talk about that next chapter. Basically, it makes the electric fields in the neighborhood of the electrode really strong enough to rip electrons off. In the absence of that counterion atmosphere, the electric fields are much weaker. They're not strong enough to rip electrons off. So you can't do electrochemistry in air. You can't do electrochemistry in normal non-ionic solutions. You can't do it in gasoline. You can't do it in alcohol. You can only do it in, well, mostly in water or other solvents that can support free ions in solution. So very important. And then I mentioned this before also, but if you've got a bunch of ink or milk or other kinds of colloidal suspensions are basically solutions that have great big particles in them, not just molecules. Then those big particles repel each other because of their surface charges, but that repulsion is screened largely by the counterion atmosphere that comes around. And that's true for things like cells, too, and a whole lot of other things. There's a vast area of sort of practical chemistry and industrial chemistry that relies on understanding how these screening layers work and what controls them and what effects they have. Okay, so that was the first case. We considered just a flat plane, and that's useful because, yeah, a lot of things are approximately a flat plane, you know, in over small areas at least. Now let's consider the case that's of most interest for chemists. That's where you've got an ion in solution, and you want to know what the counterion atmosphere looks like around that ion. Here's the solution for that case. Again, there's a bunch of constants in front that don't matter. And then there's this functional part that tells how the counterion atmosphere changes with distance away from the central ion. So here's your central ion. Here's distance away from the central ion. And what this is telling us is that the potential, and therefore also the charge density, that is the counterion atmosphere, same function, decays, but like 1 over r, that's a slow decay. 1 over r is not very fast. And then also with an exponential decay, e to the minus kappa r. That's very reminiscent of this exponential decay that we saw up here for the flat plane case. It's basically the analog for a spherical system to the flat plane case. And look, our constant kappa is appearing again, and that kappa is still 1 over the Debye length, and so it controls how thick and how big the counterion atmosphere is around each and every ion in the solution. They're all basically about 1 Debye length. in size. And again, that's about a nanometer. So there's a little counterion atmosphere of about a nanometer thick surrounding every ion in solution inside an ionic solution. Let me say something more. If you had this same ion, but it was in vacuum, vacuum, there we go, then the potential would have some constants, but it would be proportional to just 1 over r. And so this extra thing on top, e to the minus kappa r in ionic solution, is the screening factor. It's the extra factor that accounts for the fact that there's a counterion atmosphere around everything. And it makes the interactions between ions much shorter than it would be if there were no screening. Before we go to the next topic, let me point out something that isn't obvious, though you could prove it. I think there's a homework problem, in fact, that asks you to prove it, that the amount of charge, the total amount of charge in the counterion atmosphere, in either of these two cases, in fact, in all cases, always exactly cancels the original charges that caused the counterion atmosphere to start with. So you've got a central ion of, let's say, +2 for the sake of argument. There'll be -2's worth of countercharge in that counterion, spread out in that counterion atmosphere. And it will exactly cancel that central charge every time. All right, and that leads us to screening, which is a word I've been using already. It basically is the idea that, well, it's the consequence of the fact that I'm going to talk about down here. So let's suppose I have a bunch of charge arranged as a central ion plus the counterion atmosphere here. The net charge in that whole thing is 0, right? If I add up all the charge in the central ion and all the charge in that counterion atmosphere, I get 0. What kind of interaction will a new charge that you bring up from outside see? Well, it turns out that charges and also gravitational fields have this weird and useful property that if they have a radial distribution like this, then the charge seen by, or the interaction seen by this outer test charge is the same thing as if you summed up all the charge that was inside of the radius of that test charge and put it at 0, put it at the origin there. This interaction down here is the same as this whole complicated interaction up here. And that means that if this counterion atmosphere is canceling completely the central charge, and this guy is way outside the counterion atmosphere, this is 0, and you get no interaction. And so, in a screened environment like this, here's the conclusion, here's the bottom line. Two ions can only interact if they penetrate inside of each other's counterion atmosphere. So here you've got a positive charge with a blue counterion atmosphere. Here's a negative charge with a red counterion atmosphere. They're both inside of the counterion atmospheres of each other, which means they do interact, but they only interact, right? This plus charge only sees the net charge that's inside this whole inner sphere. In other words, all this countercharge here is largely canceling most of the charge on this negative ion here. So, even when they do penetrate inside each other's counterion atmosphere, the interactions tend to be weak. And so, bottom line from all this whole section, the electrostatic interactions are very strongly reduced by screening. when ionic strength is appreciable. In other words, when you're above a few millimolar worth of ion concentration. On the other hand, that occurs, the interactions are weak, because the ions have already paired up. They're all statistically paired, and that means that their effective concentration is lower than what you'd expect if you were just calculating concentration naively. And that means the activity of the ions is smaller than the molar concentration of the ions. In other words, the activity coefficients for the ions is less than 1. And it effectively reduces, it makes the effective concentration less than the true concentration. Finally, before we leave this last section here, I think, we want to talk more about actually doing calculations in order to calculate especially this Debye length and this kappa, basically. And that involves understanding this idea of ionic strength. Here's our kappa constant, which we've seen is closely related to the Debye length, and we've seen the Debye length is a really important quantity. This is just from above. I just copied it down here. And I've rewritten it a little bit to make it a little bit easier to work with, but the main point is that all this stuff here is just fundamental constants. It's always the same in every situation and doesn't change, so we might as well compute those once and for all and leave it. The stuff that varies from one situation to another is this quantity called the ionic strength, the temperature, and the dielectric constant of whatever solvent you happen to be working in. You're almost always working in water, and that's 78.4 for that. Oops, 70. There. 78.4. Unitless. Dielectric constants are unitless. And so we know the temperature is around 300 K usually. What's this ionic strength? That's the next thing we have to calculate. Here it is, or that's the next thing we have to define. Here it is. Here's how it's defined. Ionic strength is 1/2 times a sum over all the types of ions in solution. So if it's sodium chloride, there's 2 types of ions, sodium ions and chloride ions. And this sum would just have 2 terms. If you've got more kinds of ions in solution, then the sum will have more terms and so on. But it's just a sum over however many different types of ions you have in solution of the bulk concentration of each ion. So for sodium chloride, 1 molar sodium chloride, let's say, this would be, say, the concentration for sodium plus ions, and it would be 1 molar. And then the next term would be a 1 for chloride ions, and it would also be 1 molar. And so this is just, all these concentrations are just the normal concentrations that you'd expect in an ionic solution, multiplied by the charge on the ion squared. If it's sodium, where the charge Z is 1 plus 1, squaring it just gives you a 1, and this is just the concentration left alone. If it's chloride, same thing. It's -1 now, but you're squaring it so it becomes +1 again. And again, it's just the concentration of chloride. But if it's something like a magnesium 2+ ion, then Z is equal to +2. And then this becomes a 4. And it multiplies the effective concentration here. So it multiplies its effective concentration by 4. And that means that the ionic strength is not just the concentration of ions in solution. It's a specially super duper weighted average of concentrations in solution, weighted by Z² factors. And the bottom line for that is that ions with high charge, like ±2 or ±3, contribute much more strongly to the overall ionic strength than you would expect just from their nominal concentration. So watch for that. All right, let's look at some examples of ionic strength, because we're going to need to calculate ionic strengths over and over again in order to use any of the formulas down below. So for sodium chloride, +1, -1, that's a 1-to-1 salt. Here's Z for sodium is +1, Z for chloride is -1. The concentration of sodium chloride, let's call it C, Well, that's going to be the same as the concentration for either sodium or chloride after the ions come apart. And so the sum has only two terms. It's got the concentration of sodium ions times Z squared for sodium ions plus the concentration for chloride ions times minus 1 squared for the Z of chloride ions. Both of these are just C, right? So all of this just ends up being 2C, and you're dividing by 2, so it just ends up being C. So for one-to-one salts like this, the ionic strength really is just the concentration. That's the one case where ionic strength really is just concentration. It's the only case, though. Let's look at magnesium chloride now. This is a 2-to-1 salt, right? Plus 2 on the magnesium, minus 1 on the chlorides. So Z for magnesium is plus 2, Z for chloride is minus 1. Concentration for chloride is the same as the concentration of the magnesium chloride itself. Concentration for chloride is twice the concentration of magnesium itself because there's 2 chlorides per magnesium formula unit. That means that when we calculate ionic strength, we've got the concentration of magnesium here times Z squared for magnesium, which is a 4. Then we've got 2 times the concentration of this is concentration of chloride, right? It's twice the concentration of magnesium times the Z squared for chloride, which is just a 1 again. That means 4 plus 2 here is 6, divided by 2 is 3. The ionic strength is actually 3 times the nominal concentration of magnesium chloride in solution. So the ionic strength is quite a bit bigger for a case like this where there's even just 1 plus 2 ion than just the nominal magnesium chloride concentration. If we go to something like iron 3 chloride here, then it's even worse. Now the charge on the iron is plus 3. Charge on the chloride still plus 1 or minus 1. And going through the same logic as before, you've got this Z squared for the iron ion, and that's a 9. And then you've got 3 because there's 3 chloride ions. The 9 plus the 3 is 12. Divide by 2, and that's 6. And so the ionic strength for this solution of this salt is 6 times bigger than the nominal concentration of the salt in solution. All right, so bottom line, I is much greater than normal concentration for anything other than a 1-to-1 salt. Again, it's because of those Z squares that appear in the definition of I. All right, finally, let's see if we can calculate Debye lengths in some not horrible way. Here's the formula for kappa, actually kappa squared. It's got all these constants in it, and this is, this one, for example, is 8.85 times 10 to the minus 12, and they all have to be put in SI units, and this is 6.02 times 10 to the 23rd. So it's a mess of a calculation, but it's all fundamental constants. And so let's just gather all the fundamental constants together, separate out all the stuff that changes from situation to situation. And if you do that, then you get this number, 2.531 times 10 to the 5th. Units on that number are degrees Kelvin divided by nanometers squared divided by molar. That means you want to use molar units for ionic strength. That's unitless, and you want to use Kelvin units for T. And you're going to get out units of 1 over nanometers squared for kappa squared, which means you're going to get units of nanometers when you take the square root and turn it upside down in order to get Debye length. Here's the actual Debye length, so it's 1 over the square root of this up here. And here's the new number. I just did the same thing, 1.99 times 10 to the minus 3 nanometers. And then these weird units here that are basically necessary to get nanometer units out for the Debye length. That's a nice formula. It works in all cases. I haven't assumed water, for example. I haven't assumed 298 K for the temperature. So if you're not at 298 K, this is the formula you've got to use. If you're not in water, this is the formula you've got to use. But the vast majority of cases are in water, and most of them are at 298 K too. Then epsilon is 78.4, T is 298 K, 298.15. If you plug those numbers in and then redo the calculation, you get a Debye length that's 0.304 molar to the 1/2 nanometers. This now, ionic strength is in molar units usually, or at least I think that's what you want to use every time. You're taking the square root of it, and so that's going to cancel the molar to the 1/2 units up here, and you're going to end up with nanometer units for your Debye length. Here's an example of an easy calculation. Let's suppose it's 1 molar ionic strength. Then putting a 1 in there, you get 0.3039 nanometers, which is 3 angstroms for the Debye length. If instead you put in not 1 molar, but 100th molar, then the square root of 100th is a 10th, and you get 10 times bigger Debye length, 3 nanometers now. And that's pretty much the range of typical Debye lengths that you see in most situations. All right, we'll stop there and talk about the effect of ionic interactions on activity coefficients in the next lecture.